on the 26th at noon, Driving the Electric Vehicle Future with Corey Campanese. And then next Thursday, People's University again, 7 p.m., Dinosaur Family Tree. Tuesday, August 2nd, Bob Gaudio will be here to do his coffee house music session, The Troubadour. And tonight we're doing, I can't remember. What are we doing? What? You better look back there. Yes, it's Dino-Palooza. Woo, no music, but they dance anyway. Isn't it fun? Please do not feed the dinosaurs. Yes, right? Round of applause for T-Rex and Triceratops, better known as Julia and Nan. Okay. Yeah, dinosaurs, ladies and gentlemen. Okay. Now we conduct a little business. First of all, our friend Erin is here tonight from Belair Public Library. She's in there. I put her to work because I needed help. And if you go to Belair, where we have reciprocity, meaning you can sign up for free for a library card and get access to all their stuff, she'll give you one of these dinosaur kits where you can put together fossils and all kinds of fun projects. Feel free to take a look at this one if you want to when we're done. And there's a brochure here called Getting a Library Card from Belair. That's the important part. Okay, just a couple more things. The first 50 to register tonight got gifts. And I see that not everyone who signed up has come, so we're going to give them a few more minutes while I talk. Otherwise, I'm going to give the stuff away to everyone else who's here. How many people have not gotten the free gifts? 1, 2, 3, 4, 5. Roughly 10, so I think we should have enough for everyone, but we'll do it in an orderly fashion. And if you don't get something, I will give you something. So. Now, 2 more things. We're drawing a winner of a free family pass to the Carnegie Museums of Pittsburgh. This is from the people who put their pictures with our dinosaurs, the ones up here. So I'm just going to draw a name. And next week we'll give away a $100 gift certificate to Public Market here in Wheeling. The winner tonight is Christina Richards and family. So they'll get the family pass. And you can still qualify next week. Just get your picture tonight with a dinosaur and post it with hashtag I love OCPL. Uh-oh, somebody's here. So let me get their names. I'll take care of that. The first 20 people who come to all 7 classes, the first 7, get to go on our field trip to the Carnegie Museum where Matthew Lamanna, who's their dinosaur guy, will show us around.
He's a rock star.
He's a rock star. He recommended Lindsay too. So, and they chose the books that you'll be reading as the best for this type of thing. Whose bell is that?
Oh, yes.
See, this is an example of what happens.
I can eat my T-Rex.
All right. Yeah, the T-Rex will attack. Without further ado, stick around after. Please wear your shirt so we can get a group picture. And those of you who didn't get a gift, we'll get that sorted out. Instructor Lindsay Kastroll, who came all the way from Pittsburgh to be with us tonight, is a paleontology student and museum volunteer with a special interest in, guess what? Dinosaurs. Following her recent graduation from California University of Pennsylvania with degrees in biology and geology, she will be attending a master's program in biological sciences at the University of Alberta starting this fall, where she will complete her research on ornithischian ornithischian dinosaurs. Did I say that right?
Close enough.
Close enough. Things like Triceratops, we have one here tonight. Ankylosaurus and Stegosaurus. You got to start volunteering with the Carnegie Museum of Natural History, writing Mesozoic Monthly, a series of deep dives on prehistoric creatures for the museum blog. Ladies and gentlemen, Lindsay Kastroll.
Hello. So you'll have to forgive me, I'm a little bit nervous. So, welcome to the first class in the People's University Dinosaurs, where we will be talking about what exactly is a dinosaur. My name is Lindsay Kastroll, and he already mentioned all of this, but I'm wearing the same dress as in that picture, so that's embarrassing. But I do have a bachelor's in biology and geology, and I'm going to be going to University of Alberta soon to start my master's in biological sciences, specializing in systematics and evolution, which is just a lot of words for paleontology. So here's some of my other nerd credentials, just so you know I'm not full of coprolites. I'm a lifelong dinosaur nerd, volunteer at the Carnegie Museum of Natural History. I did work on a Minecraft dinosaur mod in high school, and I do writing on a video game about dinosaurs called Prehistoric Kingdom. So I have definitely gotten around in some paleontology circles online.
I'm going to turn your volume up a little bit.
Yeah.
Okay. Mic check.
Any better?
Okay, try again.
Hello.
Stay close to me.
Okay. So, long story short, a dinosaur is any animal that is within the taxonomic group Dinosauria. Obviously, that is not a very helpful or useful definition. What exactly is a taxonomic group? How does one get invited to such an exclusive club? You know, none of that is really included in the scientific concept of what a dinosaur is. Part of a paleontologist's job is figuring out how the things that they find are related. This is the essence of the study of phylogeny, the study of evolutionary relationships. When it comes to animals that are alive and modern, like cats and dogs and things like that, we can use genetic samples, DNA, to see how close the genes are across different species. But when an animal is fossilized, all that DNA goodness goes away because it's all turned into rocks. Rocks do not carry genetic information, so we have to rely on other things. Paleontologists will look at physical features of the fossils that they find. Shapes of the bone, different textures of the skin impressions that they find, lots of different things. So, you know, does the skull have a frill? Do they walk on 2 legs or 4? How many vertebrae are there? It's a lot of things. There's a lot of bones in the body. And certain traits will include or exclude an animal from specific groups. So, for example, circles and squares. Circles are round, they have an infinite number of tangents that can go around the circumference. And by contrast, squares have 4 straight sides with 4 90-degree angles. So they are kind of just mutually exclusive categories. But if you find a new shape that has maybe 5 sides and 5 angles, you can kind of assume that it's going to go into that square box because it shares the most traits with that one. But it's a lot more complicated than that. Of course it is. Phylogenetic groups aren't mutually exclusive like circles and squares. A lot of these groups are very closely related, and many of them are within each other. So taxonomy looks more like this. Welcome back to geometry class. Sorry to scare you. So this is a cute little cladogram that I drew up the other day showing the relationships between some 4-sided shapes. A cladogram is a paleontology nerd's best friend. It's a diagram that shows the relationship between different things. So You might have heard the old adage that all squares are rectangles, but not all rectangles are squares. So, looking at this graph, you can see that squares and rectangles are up there, but also nested within the rectangle group, which looks a little funny. The squares are rectangles. They have all the same traits as a rectangle, except they've evolved one more. They all their sides are the same length. So that's why squares and non-square rectangles are separated like this. The squares and the non-square rectangles have different genes that put them in different groups, but they're all related under that rectangle group. If we go back a level, we see four-sided shapes with two pairs of parallel sides. And when we have a shape that is a four-sided shape with two pairs of other parallel sides, it will either have 90-degree angles or not 90-degree angles. That's the point where it diverges. But once something kind of chooses or evolves to have 90-degree angles or not, it doesn't stop being a four-sided shape with two pairs of parallel lines. A square is still a rectangle, is still a four-sided shape with two pairs of parallel lines, and so on and so forth. So the fact that humans are great apes is a very well-established fact in scientific literature. You might have heard arguments like, humans can't be great apes because great apes are still around. Or humans used to be great apes, but we evolved so much that we stopped being great apes. But phylogenetically or taxonomically, the words are kind of interrelated. Those arguments don't make sense because, as you can see, all of these groups are nested inside of each other. So one successive group falls inside the group that preceded it. So humans are great apes, so on and so forth. Squares are rectangles, and so on and so forth. Ideally, a cladogram will have so much information that the evolutionary relationships can be traced back all the way to a common ancestor. This cladogram only goes back to four-sided shapes with at least one pair of parallel sides, which isn't very exciting. But if we had more information, we could go back to four-sided shapes in general, and then all shapes made out of lines, and then straight lines themselves, and the dots that form all lines ever. So those dots would be our common ancestor. And then going from that common ancestor, you could look at different groups that aren't featured on this specific cladogram. You could go from the dots to curved lines to circles and end up at a different group that is still related to squares and rectangles and four-sided shapes through that common ancestor. So I know this is a lot, and kind of phylogeny and taxonomy is all pretty annoying. So is everyone following so far?
Yeah.
Yes. Yeah. Cool. Is there a no? Okay. So family trees and cladograms are very similar, as you might have noticed when I was talking about them, but there are some key differences. So looking at this Star Wars family tree that I put together, you can see that two parents come together and make one offspring or more. They kind of work like addition. Sorry for the math references. I didn't mean for this to happen. But then cladograms are kind of the opposite. They work by division. You'll have one common ancestor that separates or diverges into two different groups. So for example, I don't know if I can, hey, there's my mouse. This point right here is where we have fish. And the fish diverge into ones that have cartilaginous bodies, which are sharks and rays, and fish that are more bony. And the bony fish will then diverge into lobe-finned fish, which are like coelacanths, if you've ever heard of those, or ray-finned fish, which is most other fish. So you're going to keep branching off and branching off and branching off instead of coming together, coming together, coming together. So what traits put an animal in the group Dinosauria? Going back full circle, it's been a minute since we talked about dinosaurs, I'm sorry. But I promise this is all relevant to where I'm going. Keeping in mind what we just discussed, Think about what traits you consider necessary for something to be a dinosaur. Cladographs work by division. What features divide dinosaurs from other different animals? The scientific definition of a dinosaur, those traits that are required to be considered a dinosaur, often conflict with the public definition of a dinosaur. What you all might think is a dinosaur might not be something that is in the group Dinosauria, or vice versa. There's things that you might not think are dinosaurs, which actually fall within that group. This is a very common problem, especially when you see movies like Jurassic Park that have lots of different animals in them, that doesn't actually explain what any of them are. So we often have a lot of confusion about what is and isn't a dinosaur. So that's why I made this lecture. So for the rest of the lecture, I'm going to make this a game. I'm going to show you pictures of animals, and I'm going to ask you whether you think it is or isn't a dinosaur. So don't worry, I'll start out with the easy ones. And after each one, I will pause and we will discuss what traits are visible on that animal that help scientists sort it into different groups, whether it's Dinosauria or something else. And you're going to see pretty quickly that there are some very, very reliable clues that will help you get that answer right pretty much every time. So this is a game that I've played at the Carnegie Museum at tables at events, and I've seen other science communicators do it online with their museum staff and museum visitors, and it's always super fun, leads to great discussions and a lot of great discoveries. Is everyone ready? So I told you we'd start with an easy one. Is Tyrannosaurus a dinosaur? Yes, right. So Tyrannosaurus is a dinosaur, is the quintessential dinosaur. We all know in our heart of hearts that it is a dinosaur, but let's take a closer look as to why. So there's lots of little things that paleontologists could nitpick over on the bones, but not a lot of those are readily apparent on the outside. So I'm going to give you two big clues that you can use, no matter what you're looking at, whether it's a picture or a skeleton out in the museum. So first off, dinosaurs are reptiles. We can tell that it's a reptile based on its body covering, scales, or sometimes, depending on how the artist decides to portray the T-Rex, you could have feathers. But if it isn't a reptile, it isn't a dinosaur. All dinosaurs are reptiles. Second, and this is a really big one, those hind legs are positioned under the body. So take a look at that hind leg arrow over there. It's tucked in right under its hips, just like ours. So, legs under the body is a very good adaptation for efficient movement. If you think of like a salamander whose legs are splayed, they kind of walk like this and twist their whole body while they're moving. And it actually constricts their lungs a little bit and slows them down, so they don't get to move as fast or for as long. So mammals and dinosaurs both evolved hind legs positioned under their hips for that really good efficient movement. So we're not related to dinosaurs at all, but that is a thing that we call convergent evolution, when two completely separate groups evolve a similar trait. Another example of this would be like dolphins and sharks. They're very similar looking. They have that torpedo-shaped body, but they're not closely related at all, just because that shape of the body is very efficient for moving through the water. So here's another one. Is the woolly mammoth a dinosaur? Anyone want to tell me why? Yeah. So woolly mammoths are mammals. So some people assume that woolly mammoths and other mammals that are extinct are dinosaurs just because they're extinct. So their definition of dinosaur might include the word extinct. There's a very big reason why that mammoths aren't dinosaurs, and that's because they're mammals. They're not reptiles. All dinosaurs are reptiles. No mammals are dinosaurs. So dinosaurs lay eggs and are covered in scales or feathers, and mammals give birth to live young and are all covered in some sort of hairy body covering. Reptiles and mammals diverged way, way back, like 300 million years ago. And their common ancestor is something called an amniote. An amniote is an animal that has an amnion, which is a thin membrane surrounding the embryo to keep it from drying out. Before that feature evolved, things like amphibians required their eggs to be by water because they would dry out without the water. So the amnion allowed these animals to move away from water and live in different habitats. So they really exploded and got to take over different areas of the planet just because their eggs could prevent themselves from drying out. And so that amniote common ancestor produced two different lineages, the ones that became mammals eventually and the ones that became reptiles, like dinosaurs. You just have to go back 300 million years to find them. Now, dodo birds. Are dodo birds dinosaurs? I'm hearing some mixed signals. So why do we think no? Because they're mammals? Do dodo birds have hair or do they have feathers? Feathers. They can't fly, no. Now why do we say yes, some of the people over here? They lay eggs. That's good. Dinosaurs, birds, reptiles, they all lay eggs. So those of you who said yes, you're correct. Dodo birds and all birds are actually dinosaurs. Specifically theropod dinosaurs. That's the group that includes things like Velociraptor and T-Rex. So we'll discuss theropods and other kinds of dinosaurs next week with the family tree discussion. But I just wanted to show you some of these guys to kind of illustrate how that transition between non-bird dinosaur and bird dinosaur happened. So we can see that, all the birds that are outside have their legs tucked under their bodies, they have scales on their legs, and there's even some debate over whether feathers are actually just really long, fluffy scales. But, so these guys on the screen behind me are called Eosinopteryx, that's the more dinosaur-looking one, and Confuciusornis, which are these cute little guys over my left shoulder. So Eosinopteryx doesn't look very much like a bird other than its big feathery body. It has a long bony tail, it still has teeth, but it has those feathers on its wings even though it can't fly. Confuciusornis is not a bird, but is about as close as you can get without making that transition. It doesn't have the bony tail, it doesn't have teeth, but you can still see those little tiny fingers peeking out under its wings. A modern bird, all of those little hand bits fuse together in one structure, and all the feathers actually branch off of that one structure to make that wing. It's very different from something you would see like a bat, which is their entire hand makes up their wing. So if birds are dinosaurs, that also means that birds are reptiles, because dinosaurs are reptiles. So going back farther and farther, you're going to get some real crazy things happening with phylogeny. So remember our squares and rectangles. If you've ever heard someone say that birds aren't dinosaurs, they're just evolved from them, we know that that doesn't really work out. So our crocodilians dinosaurs are crocodiles, gharials, alligators, caimans. I'm hearing some yeses. Yes? Why do we think yes? Hearing some chatter. So crocodilians are reptiles, that's true. They have scales and scutes all over their body, but they are not dinosaurs. Birds are the only surviving modern dinosaurs. The crocodilians are actually their closest relatives other than birds. So this big guy on the screen behind me, this is Sarcosuchus. It's one of the largest crocodilians ever discovered. It's eating this poor little dinosaur, which isn't very little. And if you look at its back legs, they are super splayed to the side. If you see a crocodile walking, it is going to do that back and forth shuffle that I mentioned earlier. Compared to that dinosaur whose legs are tucked under its body and flailing very frantically, that one probably can move very fast if it wasn't for the fact that Sarcosuchus jumped out of the water at. So dinosaurs, crocodilians, and a few other groups of animals are all contained in one big group called archosaurs. The Archosauria, there's a bunch of different traits that unite these animals that are on the skeleton again that we can't really see and most people don't really care about. But it's things like tooths being set in deep sockets and specific holes in the skull and things you wouldn't see unless they're really, really dead. Wouldn't help you in the field if you're trying to figure out if something's a dinosaur or not. It's boring. Now, how about this one? Is Pteranodon a dinosaur? Yes? I want to hear from the yeses. Why do you think yes? Not hearing anyone responding. What about the no's? Why do you say no? What's that?
He didn't see it.
Now, Pteranodon is an animal called a pterosaur. Usually people call them pterodactyls, but that is not it's not the scientific term for them. The scientific term is a pterosaur, and pterosaurs are not dinosaurs. They're actually a separate group, just outside of Dinosauria. Lots of people call them flying dinosaurs, but they're just flying reptiles. Dinosaurs and birds aren't the only animals that learn how to fly, just like bats. Pterosaurs are super interesting for tons of different reasons. First of which I would say is the wing itself. You know, I said birds earlier have that fused structure that all of their feathers come off of to make the wing. Instead, pterosaurs, they fly on their fingers. So this little bend right here with my little mouse, that is its wrist. This right here, these little nubs, those are its hands. And all this down here is its little finger. So with that little finger, super duper long, there's a membrane that comes off of that hand, attaches to its side, and then goes down to its leg. And look at that leg. It's sticking out to the side. It's not under the body like a dinosaur's would be. So even when they're standing, pterosaur legs are slightly splayed, kind of squatting all the time. So they don't have that key feature that we look for, those erect hind legs. They're also super interesting because they have this weird filamentous covering called pycnofibers. They're not quite feathers, not quite scales. They're somewhere in between. But obviously, they don't use those to fly like birds do. They use it to keep warm, make themselves more aerodynamic. So it's a very different sort of flight pattern than you would expect in a bird or a dinosaur. Now, have I made you question everything yet? Is Stegosaurus a dinosaur?
Yes.
Yeah, that one should be easy. So Stegosaurus is in fact a dinosaur. It's a dinosaur for all the same reasons as T-Rex. It's got scales, it walks on hind legs tucked under its body. It has armor all over its back, it eats plants and stuff, so it's obviously not the same kind of dinosaur as T-Rex. It's in a very different group. But talk about that next week. So since Stegosaurus is quadrupedal, it walks on 4 legs instead of 2, we can take a good look at its forelegs. Hind limbs are really good for propulsion. They're what push us around when we're running, even us who walk on our hind legs. But forelimbs don't need to take advantage of those upright benefits, the propulsion benefits you get from having those erect limbs. So they can do different things. They're shock absorbers when you're running on all 4 legs. They're stabilizers, they're shovelers, they're grabbers. They can do lots of things. So it makes sense if they're in sort of a semi-crunch posture, just like the Stegosaurus up here behind me. Because whenever you've got a weapon on your butt, you need to be able to pivot really fast to make sure that you can smack the Ceratosaurus that's trying to eat you. So that's why those bent front arms are really, really useful. And they're not, it's the hind limbs that need to be erect, not the front ones. Now, I saw Jurassic World last night. Finally. And it was an empty theater. It was 10 o'clock at night, no one else was in there, so it was really great because I got to heckle the movie as much as I want and cheer as much as I want. The point that I heckled probably the most was every time the Mosasaurus was on the screen because it is absolutely ginormous and shouldn't be. But is Mosasaurus a dinosaur? Yes? No? Why do you say no? Why do we say no, guys? Yeah, yeah. So Mosasaurus has its legs off to the side, and this one was a little bit mean of me because I didn't really explain it going into it, but all dinosaurs are actually terrestrial animals. They live on land, except for some very, very specific versions like penguins. Penguins are very adapted to water. Everything else, pretty much on land. So that's why, if you see a dinosaur, it's got to have feet on its legs. It can't have fins or flippers. Mosasaurus and their kin are marine reptiles, not dinosaurs, and they're actually squamates. Squamates is the group that includes lizards and snakes. So this guy behind me is more like an iguana or a monitor lizard than is a dinosaur. And some people will even draw it with that forked tongue that you can kind of see in the picture behind me. It's just like a snake or a lizard. But they aren't dinosaurs. They're not even archosaurs like the crocodiles. Squamates are a completely different kind of reptile. So we've seen 7 different taxa so far, 7 different groups. I've told you about how they're related, but I haven't really demonstrated it on a cladogram, so I just wanted to put it into a picture form, just so it's a little easier to see. I like to think so, at least. So up here we've got our theropods, the birds and the T-Rex, the non-bird dinosaurs. They, like I said, the squares have different genes from the rest of the rectangles, but they're still in that same group, so that's why they're up here together in the theropoda category. If we go back one level, we get the other dinosaurs like the Stegosaurus. If we keep going, we leave the dinosaur group and we find the pterosaurs. And further back, we get to the archosaurs, where crocodilians are involved. Archosaurs have 2 main branches. There's the crocodile side and the dinosaur side, or dinosaur and pterosaur side. So that's why we have to go all the way back here to see the crocodiles. And if we keep going, we get to the other reptiles, like Mosasaurus and the squamates. And then even farther, we see the amniotes, who split off into reptile line animals and mammal line animals, like mammoths. So let's do a little check-in. How's everyone doing? Are we feeling good? Thumbs up. Anything I can explain better before I keep going? No hands? Okay. So, what about trilobites? No? This one should be pretty easy because trilobites are these little pillbug-like creatures that live underwater. They've got this hard, crunchy exoskeleton like a bug. So, of course they're not dinosaurs. They're arthropods, just like insects and crustaceans and spiders and things like that. They have that hard exoskeleton made out of chitin. They have those antennae. They have a zillion little legs. And all of their organs are inside their bones instead of their organs being around their bones like we do. And of course, they live underwater. And if it's in the water, it's probably not a dinosaur. So what about this guy? Diplodocus. Yeah, I hear a lot of yeses. That's good. So, help. So, no. Okay, cool. Is Diplodocus a dinosaur? Yes. This one's very near and dear to my heart and all of the other Pittsburghers' hearts because it's the mascot of the Carnegie Museum. We've got a big old statue of Dippy the Diplodocus outside the museum, and it wears cute little scarves on Steelers game day and over winter. I love it. Now, Dippy is a dinosaur for all the same reasons as T-Rex and Stegosaurus and birds. This is part of the presentation where I got really tired of putting those little arrows pointing at the hind legs and everyone. Diplodocus belongs to a group of dinosaurs called sauropods, which are those really big bodied, long neck ones that you see pretty much everywhere. You get Brachiosaurus and Apatosaurus and Dreadnoughtus, and are all in the Jurassic World franchise. So very, very distinct dinosaurs, all with those hind legs tucked under their bodies. Now, are turtles and tortoises dinosaurs? No. We're getting good at this. So turtles and tortoises, which are all technically turtles, they're all in the same turtle family, are not dinosaurs, even the ones that live on land. They're often jokingly called modern dinosaurs, but while some dinosaurs will have armor embedded in their skin, turtles have those shells that are fused to their bones. They're part of their body. If you try to take a shell off of a turtle, it's going to be severely injured or most likely dead. So the group that turtles belong to, which is, I think, pronounced Testudines, I'm not entirely sure. There's a lot of reading involved in paleontology and not a lot of pronouncing things sometimes. So they're yet another kind of reptile. They're not squamates, they're not archosaurs, they are something else. What about Elasmosaurus, these Loch Ness monster looking guys? I heard a yes. Why do we say yes?
No.
No? My friend up here says not a dinosaur. He would be correct. Elasmosaurus is not a dinosaur for the same reasons that Mosasaurus is not a dinosaur. It lives in the water, it has flippers. But also, Elasmosaurus and Mosasaurus are not closely related at all. They are completely different groups. While Mosasaurus are squamates, Elasmosaurus, like Plesiosaurus, or Plesiosaurus like Elasmosaurus, are actually closer related to turtles. You can't really see it on like these Loch Ness monster looking guys, but some of their relatives actually do have shells and that look very turtly. So it's a wild, wild world out there in the fossil lands. So, yeah, I didn't even have to ask the question. Triceratops is definitely a dinosaur. So, so hopefully you're confident about that. I heard so many yeses that it should be good. Ceratopsian dinosaurs, like Triceratops, are known for their horny bone frills and horns. And their forelegs are kind of bent, just like that Stegosaurus we saw earlier, so it helps them maneuver well and manipulate their environment. But their hind legs, those all-important hind legs, still tucked under the body. How about Dimetrodon? Yeah, because it's a big fan of Dimetrodon. I'm hearing a lot of yeses. Why do we say yes?
Yes, dinosaur.
Yeah, look at the legs. He's squatting. So Dimetrodon, I think this is the hardest one in this whole group. Dimetrodon is not a dinosaur. So he looks a lot like a dinosaur because he's got those spines on his back that look a lot like Spinosaurus. But here's a fun fact. Dimetrodon is actually closer related to us than to any dinosaurs. So we don't know if Dimetrodon had scales or smooth skin because it's in that weird area of mammal evolution that we don't have proof of what their skin looked like. Some of its relatives had scales that we've seen in skin impressions. Some have smooth skin. It could even be furry, I guess. I'm not sure. But once amniotes divided into those reptile side animals and the mammal side animals, this was one of those early groups that came out. He lived way before dinosaurs were ever around in the Permian period. And so they've got those sprawling legs. They haven't evolved the mammal hips under, like the legs under the hips that we're used to. But these guys were pretty voracious carnivores, so they still got around even though they were sprawling. So, pulling us back out to the cladogram. This thing was such a pain in the butt to make.
Great.
Thank you. All these pictures are so tiny, so I apologize that they're not very easy to see up there. Way up in the corner, of course, we've got our T-Rex and birds in our theropod group. And then coming out a level, we've got Saurischians. So dinosaurs have two main groups, and I'll really go into this next week, but just to give you an idea, there's the ornithischians, which have things like Triceratops and Stegosaurus up here, and the Saurischians. So that includes the sauropods and the theropods. I know I keep going back between Saurischian and Saurischian because I had it wrong my whole life and heard someone else say it the other way, and I don't know what the right way is anymore. But it's really a difference in just the shape of the hips between these two groups. All their legs are still under their body, but it's shaped slightly differently. Now, coming out of dinosaurs, we've got the pterosaurs again. They're still the closest relatives within the archosaur group. And then the other archosaurs are still the crocodiles. If we leave the archosaurs and come all the way out here, go all the way up here, we can see that plesiosaurs like Elasmosaurus and turtles are closely related and are just outside of that archosaur group. I don't remember what this group is called, and it's probably too complicated for me to remember anyway. But that's okay, I like dinosaurs instead. But once we leave the turtle group, we come out into the reptiles, where the squamates are still hanging out, our last group of reptiles on this list. Then going back farther to the amniotes, I want to point out that the length of these lines doesn't imply anything about time. If this was showing like accurate time, Dimetrodon would be way down like over here and not up here. But it's still a different group of mammal kind of amnio than mammoths, so that's why they're separated like this. And this isn't a complete list, everything I've shown you so far. I'm leaving a lot of things out, like fish, like cephalopods and squids, amphibians. All of that would fall right in here. Anything with bones and limbs is probably going to be in here between amniotes and our crunchy little arthropods like trilobites. And hopefully this gives you a better understanding of what a dinosaur is, even if we're not covering anything or everything. But coming full circle, let's see what our working definition of a dinosaur is after establishing all those traits and distinguishing dinosaurs from non-dinosaurs and playing our little game. So what is a dinosaur? It's a terrestrial reptile with scales or feathers, no shell, and hind legs with its feet positioned under the body. This is the most practical definition I could possibly give you. It's not foolproof. There's like some weird crocodiles out there that evolved like erect posture, kind of like a horse, which are super weird. And if you ever see one, you're gonna be confused by it anyway. So, but even with those weird exceptions, this is far better than the alternative definitions. I could have stood up here and showed you pictures of skeletons and said, look at the epipophyses on those neck vertebrae, or check out the delta pectoral crest on the humerus. And it would have been less interesting, less useful, less fun. So this is the important stuff. And so I hope this is what you take away from today. So I know we're a little early, so I will open this up for questions soon. I have been talking really fast since I am so nervous. But with all that out of the way, come back next week at the same time, same place to talk about the dinosaur family tree, or cladogram, as we have learned today. And since you're all experts at identifying dinosaurs now, you know that this goofy little guy on the screen behind me is a dinosaur. But if you want to know what he is, since he's so weird, come back next week. Thanks. Thank you. I'm sure there's a bunch of questions, so let me have them. Question, okay. The kangaroo. Almost. It's kind of got that like classic T-Rex standing on the tail posture that you see in like all the old dinosaur art. They used to think that dinosaurs had to rest on their tail to keep themselves up. But nowadays we know that they have better balance than that. But kangaroos are still mammals, so we know that they're on our side of the tree and not the dinosaur side. But yeah, they do have that T-Rex sort of look, right? Yeah. Small hands. Pretty sure?
Is there any consistency to the feet?
The feet.
Because some of the things that were up there, they were dinosaurs. I didn't pay real close attention, but to the characteristics of the feet. But do they have some consistency there?
We're talking hind legs, right?
Yeah.
There is consistency in like how many toes they have usually, but they do vary a lot by group. So like those sauropods, like, there we go. These guys, their feet are kind of like, if you think of an elephant's foot, it is very cylindrical. But there's still a pad of fat under there to cushion them because they're very, very heavy and they're going to break their bones if they're just standing on them. And there's even some sauropods that lose some of the bones in their limbs, just like, or in their feet rather, to make it less likely that they're going to break something, which is very interesting. So it's kind of like they're just standing on stubs. But other than like looking at these guys, you can see the Ceratosaurus has these, very long toes that help them run very well. Kind of like a kangaroo, it's springing off of those toes every time it takes a step, compared to Stegosaurus, which has these little blunt toes and little blunt claws. Does that answer your question? Okay, yeah, it's consistent within groups of dinosaurs, but across Dinosauria as a whole, there's a lot of variation. So I see a hand up in the back that I think I missed before. What's your question, dude?
How do you know they are dinosaurs?
Well, we know that they're dinosaurs because we kind of decide that they are. When paleontologists started looking at dinosaurs, they were saying, okay, some of these animals look kind of similar, some of them don't. And so they had to make a rule that animals that are going to be in this group over here are going to have certain features, like hips or their legs under their body. So if it has legs that aren't under its body, it's going to be something else. So it's looking at a bunch of stuff and going, oh God, how do we sort this? So, and you over there?
So, is there like a certain, because Jurassic Park, again, is what we associate with a lot of dinosaurs.
Right.
May not exist. So, is it like the Jurassic era, or is it like the different era that we?
Right.
So, I know there are, I just don't know what they are. So, is it just a certain time period that classifies dinosaurs?
It's not so much a certain time period. It is all those physical features, like I was saying. But dinosaurs show up in the Triassic period. That is the first period in the Mesozoic era. There's 3 periods within the Mesozoic era. Before the Triassic, there were no dinosaurs. There were things like Dimetrodon and other amniotes and amphibians and really large insects and things like that. And then after the Triassic, that's when dinosaurs started getting really big. That's when the Jurassic period started. And we got things like sauropods, we got Stegosaurus, we got Ceratosaurus and Allosaurus. And then around the end of the Jurassic period, it turns into Cretaceous period, and that's when you see things like T-Rex and Triceratops and Giganotosaurus in the new movie. All of that, there's kind of a little bit of succession where big dinosaurs replace big dinosaurs. You don't see as many Stegosauruses after the Jurassic period. You see things like Ankylosaurus instead. I forget what your question was, but at the end of the Cretaceous, we have that meteor hit. There's a lot of crazy stuff happening around the world, and all of these big non-bird dinosaurs go extinct. And I think there's going to be another lecture about the extinction of dinosaurs near the end of the series, so I won't go too far into that. But the birds survive, so dinosaurs don't go completely kaput at the end of the Mesozoic era. Any other questions?
We have them online.
Online.
The question is, how can you tell from pilot bones about where the leg position is?
It's a lot to do with the hip sockets. I know on Wikipedia there's this really good diagram showing the difference between sprawling posture, erect posture, and pillar erect posture, which is slightly different. And it shows how the ball of the femur, that round head, goes into the hip socket. If you saw like a human femur, the upper leg bone, the one near our thigh, you see just a big old ball sticking out the side. That's what hooks into the side of our hips, and it comes straight down from there. If you saw something like a crocodile, which I'm not an expert in, so I apologize if this is a little vague, their hips definitely attach at a different angle from something like ours. So dinosaurs and us do have that convergent evolution going on where they have similar hips. Any others?
Yeah, another online question was how science paleontologists tell about the skin, whether the feathers or scales. How do they determine that? They have feathers.
Could you repeat the question?
Absolutely. So the next question was how paleontologists can tell that an animal has reptile or scales or feathers. And sometimes it's as easy as they preserve. You'll have skin impressions in certain species, or you might have actual feathers preserved. Archaeopteryx is a really famous one because of the feathers that preserve. You can see like its full wings and even its tail fan is still in that fossil, with your naked eye. So that one's definitely got feathers. But other times on things like Velociraptor, they can see little nubs on its arm bones that look like the little places where quills would attach on a bird's wing. So they can make inferences based on that. And also with things like the oviraptorids, like Oviraptor, there have been ones, like fossils that have been found where they're still in a like lifelike pose, kneeling over their nest with their arms out in front of them like this. There's not really any reason to have skinny little dinosaur arms hanging out over a nest unless there's a big fan shading that nest beneath it, keeping it cool from the desert heat. So that's another way, just by posture. And when we don't have a specimen from a specific group that has skin impressions, they will make inferences based on what it's related to. So for the longest time, we didn't have a great idea of what T-Rex's body covering looked like. We assumed it was scaly, but then we found something called Eutyrannus, which is covered with feathers. And it's still in that Tyrannosaur family. So people started thinking, maybe T-Rex is covered in feathers. And so that's the point where they started kind of making that debate and going back and forth about, does T-Rex have feathers, does it not? So it is kind of complicated. In a lot of places we don't have a good idea, but in a lot of them we do. We do have direct evidence of feathers or scales, which is great. Any other questions from the room? Okay.
How are you guessing what color the animals are? You see a book, several books, and they all kind of colors.
A lot of it's just what the artist thinks would be cool, which is fair. And I got a lot of really nice paleo art up here with a bunch of different pretty colors, you know? Like this Triceratops is very different from this one. Well, kind of. But a lot of times it's up to the artist whether they think they're going to try and make it blend in with the environment or make it stand out, like sexual selection sort of thing. Maybe they just think it looks cool. But there are specimens where we can see either with our eyes or just with like detecting instruments, the pigments still in the feathers that are preserved. There's one that I remember, I can't remember its name. It might be Sinosauropteryx or something along those lines, where if you look at this fossil, it looks like a red panda. Like the tail is striped. You can see them with your eyes, and it is crazy. So pigments sometimes do preserve. Other times, it's just guessing and having fun. You know, I could draw a dinosaur that's bright blue. It's great.
I did the green for Tyrannosaurus because it looked good on a black t-shirt.
Yeah.
I think that's very simple.
the one at the start of the presentation was bright orange, you know?
Any other questions?
Okay.
Let's see, when did you first become interested in paleontology?
I couldn't tell you. I've been interested in dinosaurs for so long, like maybe my parents would have an idea, but I could not tell you. I was talking their ears off for as long as I could remember, dragging them to the museum. They don't go with me anymore because they know we're just gonna walk around really slow. So, you know, I've got like just dinosaurs in my DNA. Any other questions? Oh, one more.
So, if dinosaur bones are basically caused by the rocks,
Yes.
how do they determine, like, and you see the Russians, which feel like things that,
Right.
being bones, so, like, how do you, I mean, one is actually exposed, and it's, oh, yeah, we're good, whatever, so how?
How do you tell the difference between a rock bone and a rock? Kind of.
I mean, yeah.
It's a good question. So, like dinosaur fossils are usually preserved in sedimentary rocks. It's rocks that are made out of things like clay or sand. And so they have a specific texture and way that they look and feel, basically. A fossil is going to be a lot more smooth because it's bone that has been replaced by minerals. So different mineral makeup than the surrounding rocks. It's going to have probably a different color and different shape. So if you see something that's cylindrical sticking out of a really grainy sandstone, then it's probably going to be a bone or some other thing that is stuck in that rock and hasn't been able to come out for millions of years. So does that answer your question? Okay.
Round of applause for Lindsay. Before we go, by our count, there are about 54 people here, so we should be close to being able to get everyone. Is there anyone who has registered but hasn't gotten their gift yet? Raise your hand. One? How many? 2, 3, 4? Come on up, those of you who registered. Get yours. And if we go over, if anyone doesn't get it, next week you will have it. That's my promise to you, or you'll have it. It will be emailed. What's your name?
That was very interesting.
Thank you.
Yeah.